Okay, today we're going to be looking at cosmology. So cosmology is a study of the cosmos, and it looks at the origins of the universe. So one theory of the origin of the universe is the Big Bang theory. So this is the idea that the universe was originally a concentrated extremely dense, small, kind of place. It was all the mass, all the energy was concentrated down in this extremely dense, small area, which we would call a singularity. It didn't, and at some point it began to expand very rapidly and became a very hot explosion. After a time, the universe cooled, and matter began to coalesce into large gas clouds, similar to like the nebula that we discussed previously. And from that, the gravitational force led to galaxies, stars, and planets, etc., forming. That's a very simplified view of the Big Bang. What we know is the universe is expanding today. And we also can see what we call cosmic background radiation, which is like it's almost like the after heat of the Big Bang. So we're going to look at these two pieces of evidence for the Big Bang in more detail. So firstly, the expanding universe. Is observed by redshift. So if you've got a galaxy here, and there's another galaxy over here, they're moving away from each other. But so the light appears to be redshifted. This is a similar. This is well, it's the same principle, same type of effect as the Doppler effect. Same idea as the Doppler effect. So the Doppler effect was when you have two sound sources. For example, when you hear an ambulance, if you're standing at the side of the street and an ambulance comes towards you and then it passes you and goes away, you hear that difference in the pitch of the sound as it comes before you towards you. That sound wave is getting compressed, but then as it goes away from you, it's like that sound wave is getting contracted, and so you hear the difference in the pitch. And the same happens with when a light source is moving either towards you or away from you at a very high speed. If it's moving away from you, you see redshift. If it was moving towards you, you would see blue shift. So let's say we've got an observer here, and you've got another observer over here. And let's say there's some kind of source. We'll have a wee star here. And our wee star is moving towards this observer. So we've got a light wave here. Now I'm going to change the colour, and we're going to go for blue, dark blue. So here, as this is coming, and all the light waves are coming, the waves kind of pile up a wee bit. They kind of get pushed together more. So the light wave is as if it's shifting towards the blue part of the electromagnetic spectrum, like that. Now if we look at, let's get a nice reddish colour, the red. So this here is going to kind of be, as this is moving away, it's like the light wave here is getting stretched. I've exaggerated this quite a lot for the effect. So it looks like it's shifted into the red part of the spectrum. So the wave coming this way is got a longer wavelength than the wave coming this way has got a shorter wavelength. So here, the wavelength decreases, and the frequency increases because the speed of light remains constant. So the observer sees light blue shifted. So that would be just the wavelength is what if something that had a certain wavelength on Earth, when it's blue shifted, it's just moved along a bit towards the blue end of the spectrum. So on this side, the source is now moving away from this observer, so the wavelength increases and the frequency decreases. So the observer sees the red shift. Now when astronomers look at distant galaxies and take a measurement of the light spectrums from them, collect the light from these distant galaxies, the vast majority of them show redshift. So that means for the vast majority of galaxies, they're actually moving apart. There are few where they do see blue shift, so that would imply that for these galaxies, they're actually moving towards us. Actually, our closest galaxy, Andromeda, is moving towards us. Astronomers have only seen around about 100 galaxies that are actually blue shifted when we observe them. And there's billions of galaxies, so that is strong evidence that everything is kind of moving apart at a high speed. and is therefore evidence of for the Big Bang. Let's look at what this would look like in the spectrum. So here, say this would be a spectrum from some light source. We'll say the sun. Now, when light passes through a gas, different gases will absorb different parts of the spectrum. So these black lines are where certain wavelengths have been absorbed by different gases, and so we can see these wavelengths are like fingerprints because they correspond to exact wavelengths of light. For example, hydrogen absorbs light at 760 nanometers. Now a nanometer is, I'll just write that in, is 10 to the minus 9. So when somebody takes a sample of the of light and they see a black line corresponding to 760 nanometers, they know that hydrogen gas is present in that star or whatever the light's been passing through. So this being able to take it's called spectroscopy, is like a fingerprint which tells you the gases that make up a star or a nebula or whatever. So this is what you would see if on Earth, nothing moving. If it's been redshifted, this line is shifted. Instead of being coming here in the spectrum, you would, if it wasn't redshifted, you'd see that line down here. It's shifted along to here. Likewise, this line that's in the yellow part of the spectrum is shifted along here. So this is what the spectrum would look like in redshift. Likewise, if it was blue shifted, you would see this red line would come down here somewhere. Galaxies, it's important to note, galaxies that are further away show greater redshift. So this implies they're moving away at higher speeds. So let's see how we would use redshift. So the equation for the relationship between the change in wavelength and the velocity of the galaxy and the speed of light is, so you have the change of wavelength over the reference wavelength. So the reference wavelength would be, for example, that signature for hydrogen, where hydrogen absorbs light on Earth is 760 nanometers. That's what we mean by the reference wavelength. is equal to the velocity of a galaxy over the speed of light. So that's the same as the change in wavelength over the reference wavelength so we can call that delta lambda, where delta means the difference between two things, over the reference wavelength is the velocity of the galaxy over the speed of light. So let's look at an example. I'll keep that up there. A spectral line for hydrogen has a wavelength of 760 nanometers. The same line observed from a distant quasar is 645 nanometers. Just to note, quasars are very distant, extremely bright objects that drown out the light from other stars in the same galaxy. The velocity of light, c equals 3 times 10 to the power of 8 meters per second. So we're going to use this equation. So the change in wavelength is 760 minus 645, which is 115 nanometers. And that's divided by the reference wavelength, which is the 760 nanometers, which is equal to the velocity of the galaxy, which we're trying to find, over the speed of light, 3 times 10 to the power of 8. So rearranging that, the velocity of the galaxy is going to be 117 times 3 times 10 to the power of 8 all over 645. Which is 73,488,372 meters per second. Now we'd put that into this form, 5.35 times 10 to the power of 7 meters per second. The other evidence for Big Bang is the presence of cosmic microwave background radiation. Now, that kind of crackly noise on the radio is the picking up of the background radiation. We call it the CMB, cosmic microwave background radiation. Now, it's detected using radio wave telescopes. So the radio wave telescopes, they detect radio waves. So it's part of the electromagnetic spectrum in that radio wave wavelength. Radio waves have the advantage that they are that they're not affected by the clouds, whereas obviously if it's a cloudy night you cannot observe, you can't see the stars, but radio waves aren't affected in this way. So they're not blocked by clouds, and you can use radio telescopes can be used day and night. Now, the cosmic microwave background radiation is very uniform. So it comes from all directions. So regardless of where you point your radio telescope, you will pick up the same signal. It'll be the same strength, and it's very, very uniform. So in 1948, the Big Bang theory predicted microwave radiation should exist as a relic of the thermal radiation originally from the Big Bang. So imagine the Big Bang, this huge, big, very hot explosion emitted vast amounts of thermal energy, and as time went on, there was the cooling of the universe. But in 1948, there was this prediction made that there should be a remnant still of this thermal radiation. They also predicted the wavelength of the radiation today would be much greater than when the Big Bang explosion, you have this thermal energy, it would be a very short wavelength and be extremely hot. But because of the expanding universe, the wavelength is much greater than it would have been at the Big Bang, and they predicted that in 1945. So today, the wavelength is in the microwave part of the electromagnetic spectrum, and the temperature is just as 2.7 Kelvin, so just above absolute zero. And that's about minus 270 degrees C. So this was all predicted. Scientists predicted that the temperature would be round about 2.7, and then in 1960 the background radiation was detected, and the temperature confirmed at 2.7 Kelvin. Also, the Kobe satellite confirmed these predictions.